Let's spend the next few minutes talking about what chemistry is, the scientific method, and using some of the numbers that are associated with chemistry and science. And so, it's an introductory general chemistry lecture. We'll start with week 1. Right? Spend some time going over the broad class goals. There's more specific goals, detailed individual outcomes located on the class website. I'll make those available to you via a link if you so desire. So let's talk about what chemistry is. At its simplest level, chemistry is the study of matter and also energy. But mostly that energy comes from the conversion of matter into new forms. Fire releasing heat. And so we have to study a little bit about transfer of energy and working with energy. But mostly it's about matter, dealing with what matter is and converting matter from one form into another. Additionally, chemistry is an empirical science. What this means is that information that we obtain in a chemical setting comes from observation and experimentation. The things we see, the things we do, come from the lab. Right? So these numbers that we glean from our work is all out of the physicality that we deal with in the lab. Our observations tell us something about what's going on. So what we have to deal with when we deal with chemistry is this idea of the microscopic, things that we can't see, and how that relates to things we can see. Right? The pressure in your tire is related to the spacing and number of molecules in that tire. So the behavior of those molecules has an impact on the bigger picture. And so that's information that we have to glean. Something going on at the microscopic level translating something that we can see out here in the real world. So a lot of this deals with experimentation and information. And so what we do to get that information, we often have to deal with measurement. Right? So measurement is a big part of what we deal with. We say it's a quantitative science. Chemistry is a quantitative science. We have to measure things, and that usually means we put a number on it. Part of the reason for this is reproducibility. We want to be able to say for certain that this coffee cup has a certain level of greenness. Free advertising. I don't get a commission for that. So the level of greenness to my eye might only be, it's sort of dark green. Right? For a colorblind person, this might not be visible at all, or be sort of a brownish color. So how do we relate or measure the greenness to say that the greenness is consistent, so that every person, every scientist would be at the same level of greenness? Again, this is where measurement comes in, quantification. And whenever you do a measurement, you deal with a factor that we call uncertainty. So let's just take a look at this paperclip. All right. How big is this paperclip? Well, I mean, that's obvious, and it's about 4.5 centimeters, right? Well, that's true. It is about 4.5 centimeters. Or is it? I mean, on your screen, it might only be this big. All right? Or on my screen, I've got to blow it up. It's like as big as my head. See? It's big as my head. All right. So is my head 4.5 centimeters? So, two problems here. First, there's two different things we deal with when we deal with a measurement. When we deal with any measurement, we have to deal with the scale we're measuring it against. So looking at that, we can see that the paperclip is somewhere between 4 and 5 centimeters large. That we can say for sure. We can say with a pretty high, according to this scale, if we ignore the fact that the scale might be different, according to this scale, the measurement says that it's somewhere between 4 and 5 centimeters large. Right. That is what we're pretty sure about. We're pretty sure that with no uncertainty that the paperclip is somewhere between 4 and 5 centimeters. Additionally, we as measuring devices can look at that scale and say, well, pretty good assurance that between 4 and 5, where roughly is that end of the paperclip? Right? We can say for sure that it's probably not, 0.1 or 0.2 or 0.3. We could probably say, well, somewhere between 0.4, 0.5, 0.6, depending on how your eyes work. So associated with that number, 4, the one we know about, 4 centimeters, is another number that we're not so sure about. That's that number we're a little bit uncertain about. We're not very uncertain. We could say 4.5 or 4.6. They're relatively close. But we can't say 4.67, not at least using the scale. The human eye is pretty good at obtaining another level of information based upon estimation. We have a number that we're sure about, the 4, and we have an estimated digit, a number we're unsure about, one that has a certain level of uncertainty associated with the measurement. So we always have to deal with this certain digit and uncertain digit. And the uncertain digit is the one usually at the end of our measurement. So let's just take a look at what this looks like in the lab. In the lab, we often will use a digital scale. All right? The problem with the digital scale is that it doesn't allow us to estimate any of the digits. The uncertainty is hidden. Usually it is the end of the number. So in this particular example, we look at it measuring 0.199 milligrams or 0.2, depending on how we look at it. The uncertainty is in that last digit, where you're measuring against a scale. Again, the uncertain digit is the estimated digit, the digit that you're estimating. If we take a look at this graduated cylinder, what we see is that we can be for certain that it's between 5 and 10, and then we can do better. We can see that it is somewhere between above 8 milliliters, but below 9 milliliters. But that's the limit of our measurement. We know that the certain digit is that it is 8 milliliters, and the uncertainty is any estimation. We can see that it's a little bit above 8. The uncertain digit is, again, the one that's estimated. Now, if we get to a finer scale, we can say that it's definitely above, a little bit above 8. How much above 8, we don't know. Again, the human eye can estimate. I would say that's about a third above, or 0.1, 0.2 0.1 or 0.2 milliliters above the unit 8. Again, that's the estimated digit. Now, when we deal with numbers in our labs and in our books, there's usually no way of showing this estimated digit, except in terms of an error measurement, the relative error within a measurement. And that's a topic that shows up in a different class. Now, if we take that same burette, if we take that same water and we dump it into a much more precise measuring device, one that has a much finer gradation, we see that yes, we're not bad. We are above. Our measurement says that the water had a volume of greater than 8 but less than 9 milliliters. And if we look at the finer scale, we see that it's 8.1 for sure, maybe even 8.15. Again, the estimated digit depends on the scale that we're able to. These digits, the number of digits that we are able to obtain in a measurement or that show up in a problem, relate to significance. And so we call them significant digits. They also relate to this idea of precision, how reproducible a measurement is. So going back. So significant figures in a digit, in a calculation, deal with the number of real, valuable digits in a measurement or calculation. Sometimes these values, we can generate numbers. Again, chemistry is not just about the numbers. We can generate numbers that actually have no meaning. The only ones that are actually meaningful are the significant digits. What do I mean by this? A good example would be the dollar bill. Right? If I say that something costs a third of a dollar, I don't say that it costs 0.333333333333 cents. I say it costs a third of a dollar, or 33 cents, or 34 cents, depending on how we round. The numbers below a penny are insignificant for our measurements. That's sort of an artificial constraint, but in many measurements, we're really limited by the number of significant figures. So in this particular example, 4.5 centimeters versus 4.56, again, the paperclip example, we can't say that it's 4.56. We're limited to 4.5 centimeters by our measurement. Now, if we get out our calipers, our measuring, a more highly calibrated measuring device, one that is more precise, we can maybe obtain a measurement with a greater number of significant figures, 4.56. Okay. Now, these measurements, the greater the number of significant figures, is a representation of precision, how reproducible a measurement is. If I give you the calipers and you take that paper clip, you should be able to measure 4.56 centimeters reproducibly. Whether I do it, someone else do it, or we can hop from scale to scale. So precision is one way of discussing our numbers. To say our numbers are very precise, that means they're very reproducible. This is contrasted with accuracy. It's very possible to reproduce a set of numbers and have them be totally worthless because you make some sort of procedural error. Accuracy is a relationship to how close to the truth the actual value is. Ideally, we want measurements that are both accurate and precise. Accuracy is something you can only obtain by repeated measurements from different sources, different scales, or different balances, or different mass measurement techniques if you're doing measuring masses. So there's the two differences: precision, how reproducible; accuracy, how true. And sometimes you have to sacrifice one to get to the other, but not always. So going back to significant digits, let's take a look at a small handful of significant figures, and we can see that we have some examples here. 1,000 versus 1,000. Where significant digits really comes into play is when you deal with zeros. All right, all non-zero numbers are considered significant. So if you have a bunch of different numbers, 1,223, this all of the non-zero numbers are considered significant. And where the gray areas are when you deal with zeros. So let's take a look at two numbers. Zeros between any real digit are significant. So if we look at this last number, 1001, 1001, the implication of those zeros is that they are real and they are significant. So this number 1001 would have 4 significant digits. But leading zeros are not significant. 0.01. Those two zeros in 0.01 are placeholders. All they are to do is represent the relative scale that we're dealing with. They aren't meant to carry significance. Leading zeros are not significant, but trailing zeros are significant if there's a decimal point. 0.01 versus 0.0100. 0.0100 has 3 sig figs because those zeros are mandatory. They are placed in there to represent that this has 3 significant figures. So, in general, numbers at the beginning, anything with a decimal point is good. Right? Zeros before, at the start of a number are usually worthless. Zeros at the end are often valuable. The only time it gets a little bit weird is when you have 1,000. When you say 1,000, is that 1,000 or is it 1,000 point? So we have to be cautious when we deal with those numbers. The easiest way around this is using scientific notation. And I've talked about scientific notation in previous slides. almost anything associated with a measurement will have its own inherent number of sig figs. Don't skimp on the sig figs. In the lab, remember, you can always estimate one extra digit than the scale you're using. The leading problem is things like temperature. You guys will read a thermometer, you'll say 88. Is that 88 or is it 88.5? You can always get an extra sig fig out based upon your scale. For an analog scale. For a digital scale, you have to, it's a little. How do you work with sig figs? Well, when you deal with sig figs, really where they come into play is when we're doing manipulations on a number. When you do a measurement, fine, no big deal. You can just write the number of digits and you'll be good. But what often happens is that we carry those number of significant figures through our problem. We really only do 4 basic operations: addition, subtraction, and multiplication, division. With addition subtraction, when you deal with sig figs, it's the old joke about the millionaire going to the grocery store. So if I go to the grocery store with a $5 bill and I buy a $1 loaf of bread, I have $4. But if I'm a millionaire and I go to the store and I buy a loaf of bread, I'm still a millionaire. All right. So when you deal with addition and subtraction, the numbers, the significant digits, are dependent on the smallest number of significant figures past the decimal point. So let's take a look at an example. If you take 15.75 and you subtract 0.0133, hopefully I put this right here. All right. We line up the numbers based upon their location on the decimal point, and when we add them, we then truncate anything past to the right of the decimal point than the least significant answer. So basically we're limited by the uncertainty in our last digit. So 15.75 0.013333 would be equivalent to 15.76, and there would be no, those numbers would be truncated. There would be no. Now, addition and subtraction is actually quite rare in the chemistry class, surprisingly. Most of what we do is multiplication. We do some addition and subtraction, so be cautious. But with multiplication and division, it's much simpler. The answer can't have more sig figs than what we originally have. So if you start with 3 sig figs in one of your problems, you're going to end up with 3 sig figs. So if we dealt with something like 15.75 divided by 0.33, this would give us 47.72, but we're limited to 0.33, 2 sig figs. So our answer cannot have more than 2 sig figs. 48 would be our answer. What this means, the practical side of this, when you're dealing with your calculations, always carry 1 extra sig fig until the end, and then round appropriately to obtain the correct number of sig figs. You start with 3, end with 3. So let's talk. Okay, why does precision matter? Why does this precision matter? Well, like I said, science is quantitative, so we have to measure value. So let's just take a look at an example. We're going to use this example of a real-world problem to discuss the scientific method. All right, the speed of light is right now is approximately 3.0 times 10 to the minus 8 meters per second. That's pretty fast. That's speed of light in a vacuum, or 3 times 10 to the 5th kilometers per second. This process was started by Huygens. And so these early measurements were starting to arrive, like 2.2 times 10 to the 5th kilometers per second was one of the earliest measurements that was obtained. Now, a series of increasingly more precise measurements have been made. But really, at the end of the 1800s, they were starting to obtain values. They were starting to get a relatively precise measurement. Now, there was, again, these numbers, if in using our rules of significant figures, you can see that the number that Huygens generated has 2 sig figs. Notice I didn't actually include the decimal point on purpose, just to show that there's 2. So the estimated digit in this case, the uncertain digit, is that second 2. Now, Foucault had developed a slightly improved method for doing this, and he obtained a more precise measurement, 2.98 times 10 to the negative, sorry, 2.98 times 10 to the 5th kilometers per second as his value. Again, that estimated digit is the 8. That could be a 9, it could be a 7, so that would mean that we're dealing with a factor of 1,000 kilometers per second different in the speed. This is where the error comes in. Now, where this is important has to deal with the Michelson-Morely experiment. The Michelson-Morely experiment is what I'm going to use to illustrate the scientific method. The scientific method is the process by which all science is generated. Now, the scientific method is the ideal. It doesn't always proceed like this, but this is what we strive for. The Michelson-Morley experiment is basically contingent upon precise measurements of the speed of light. Let's break down what the scientific measurement is and then relate it to the Michelson-Morley experiment. The scientific method is this procedure. It's based upon a number of consistent steps. One is an observation, just something we see. Right? And this generates some sort of question that we want to ponder. Right? And this question is not the science. Right? The science is what comes next. The question is answered using some made-up answer, which we call the hypothesis. The hypothesis is our answer to that question. Right? So what do we mean? So the observation, one of the observations is light. Light is a wave. Right? Light has wave-like properties. This is something that was determined early. And this wave-like properties has certain implications. And the question is, how does light travel? I mean, what we know about waves in general is like the waves on the beach or sound. Sound is a wave. Is that waves propagate through something. Waves have a tendency to propagate through water. Sound waves propagate through air. And so the question really deals with is, how does light travel? What is the media that light travels through? Light can travel through a vacuum, right? No air, and yet light still functions. So there has to be the hypothesis is that there has to be something that allows light to travel. What carries light from place to place? Right? So the Michelson-Morley experiment attempts to get at this hypothesis that light travels through something. Light travels through this fictitious thing that we call the ether. Right. So the hypothesis that the Michelson-Morley gets at is light travels through the ether, and we can tell how it interacts with the ether based upon which direction the light is traveling. What do we mean by this? If the ether is present around us, it takes place all over the earth. If this ether is present, the earth is moving through the ether. The earth is moving. So the side effect is oftentimes there's a unintended consequences that we have to deal with when we have an assumption. And the assumption again is the simple one, that light travels through a media. That media then is present all around us. That means it's present on Earth. It's present. The Earth travels through this ether in space. So we are present in a field of ether. But the Earth is moving through this field. And so what that means is that it's moving through this stationary field or a moving field, depending on how you look at it. And the fact that this ether, we are moving in the presence of the ether, means that the side effect is the prediction, and here's where the science comes in, prediction is that depending on how the Earth is moving relative to this stationary ether, light will travel faster in one direction than in the other. So this is the crux of the Michelson-Morely experiment. The Michelson-Morely experiment deals with light having a different speed based upon the direction it's traveling. Light traveling with the Earth's motion, or traveling against the Earth's motion, or depending on the season, depending on how far you extrapolate this. Now, the Michelson-Morely experiment, again, highly precise speeds of light. Right? So they needed, for this to work, the calculations based upon the speed of the Earth's movement and a few other things dealt with precision down to 0.04%. Actually, it turns out to be 0.02% measurements. Right? So they needed to have highly precise speed. So the Michelson-Morely experiments started to get at this level of precision, the percent error within the measurement, which is a topic for a whole different class, analytical chemistry. So the experiment to design was actually very novel to design how the speed of light travels. It's actually difficult to measure, but they were able to do it. But here's what's so interesting about the scientific method. The scientific method doesn't really care if the answer is right or wrong. The scientific method, all we care about is whether we answer, whether supports the hypothesis or doesn't support the hypothesis. So the Michelson-Morely experiment looked at the speed of these two beams of light, depending on one was with the movement of the Earth or one was against the movement of the Earth. And what they found is that there was no observable difference in the speed of light. So that means that the hypothesis was wrong. It does not support light traveling through the ether, doesn't depend on the speed of which direction. So that means that the hypothesis is wrong, and then you have to rethink the hypothesis. Which is really annoying for the scientists at the time, is because this ether, how do you have light, how do you have waves that travel through something? What this says is that the ether had to have other properties, or it had to have sort of divergent properties. And so this led to the whole rethinking of the ether hypothesis, and eventually led to some more modern physics that we know about. So the ether hypothesis was a failure. So Michelson-Morely is just one example of this. But this observation, question, hypothesis, prediction, experiment model is standard throughout the scientific community. So that's a quick breakdown of significant figures, why they're important, and the scientific method. Okay? We're going to be moving on into classification of matter and talking about what matter is for the next talk.